In the 1800s, a chemist whose last name is Arrhenius came up with a simple and accurate equation that relates the rate of a reaction to the temperature of the reaction and the activation energy of the reaction. Today, we call that equation the Arrhenius equation. So as you can see, I have written it out here using all sorts of pretty colors. So what this Arrhenius equation says is that the reaction constant K is equal to this frequency factor A times E to the negative E sub A, this is our activation energy, divided by R, the gas constant, times the temperature T. So the reaction constant K is for a given reaction at a given temperature, and it has units of molarity per second, or molarity times seconds to the negative 1 for zero order. It has units of 1 over seconds, or seconds to the negative 1 for first order, and units of 1 over molarity times seconds, or molarity to the negative 1 times seconds to the negative 1 for second order. So now let's talk about the units for our activation energy. Activation energy is in joules per mole. The gas constant is equal to 8.31 joules per Kelvin mole, or it could also be written as moles Kelvin. It doesn't really matter because multiplication is commutative. And then temperature is in units of Kelvin. And then we have this frequency factor. Frequency factor has the same units as the reaction constant K, and it can actually be broken down a little further. So the frequency factor is A, and A is equal to Z times P. Z is the collision frequency, and what that sort of can tell us is how often a collision results in a successful reaction. And we know that all reactions involve a collision of some sort. And then we have the steric factor P, and what the steric factor tells us is sort of the proportion of collisions with the correct orientation for the reaction to happen successfully. And these sort of both go back to the collision model or collision theory of reaction. Many times A is given to us. We don't really have to figure it out. It could sort of be figured out experimentally, but that's kind of hard to do. So if we want to find the reaction constant K and we're given A and the temperature and the activation energy, then we can just solve for it. We just plug and chug. Likewise, if we are given K, the frequency factor A, and the temperature, we could solve for activation energy, and so on and so forth. Now, sometimes A is not given to us. So if A is not given, we can actually still use the Arrhenius equation. For example, if we're given a table of K values at different temperatures, we can find the activation energy, E sub A. So let me draw out a table of sort of K values. So let's have K, and let's have this be in seconds to the negative 1, and that would be for a first order reaction. And then let's have some temperatures, T in units of Kelvin. So let's say K is equal to 1,000 at a temperature of 300 Kelvin, and then K is equal to 2,000 at a temperature of 400 Kelvin. So the way that I'm going to use this equation is just through some algebraic manipulation. We can solve for the activation energy without ever using the frequency factor at A. So we start with our equation. K equals A times E to the negative E sub A divided by R times T. And the first thing we're going to do is we're going to divide the whole thing by A. So what we get is K divided by A is equal to E to the negative EA divided by RT. So now we want to get rid of this E. So the way we do that is by taking the natural log of both sides. We're allowed to do this because in algebra, as long as we do the same thing to both sides, well, we're just allowed to do that. So what the result is the natural log of K divided by A is equal to negative E sub A divided by R times T. Now you'll notice that we've lost our E here, and that's because if we take the natural log of E to the blah blah blah, we get blah blah blah. In this case, our blah 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 is negative E sub A divided by R times T. So we just sort of drop the E from there, and then we use our logarithm rules to separate this, this expression right here out. What I mean by that is we can separate it into the natural log of K minus the natural log of A is equal to negative E sub A divided by R times T. And from here, we solve for the natural log of A. So what we get is natural log of A is equal to the natural log of K plus E sub A divided by R times T. So before I proceed any further, I'm going to sort of label these values because I think it's a good habit to solve things algebraically before you enter in numbers. So this will be K1 associated with T1, and then we'll have K2 associated with T2. So now I can write my first equation. And what that's going to say is the natural log of A is equal to the natural log of K1, that's here, and that's associated with T1, plus activation energy E sub A divided by gas constant R times that T1. And then we'll write another equation that says the natural log of A is equal to the natural log of K2 plus the activation energy E sub A divided by R times T2. So you may be wondering how we're sort of going to solve for E sub A. Well, we have natural log of A equals something here, and then we have the natural log of A equals something else here. Natural log of A is equal to itself, so that means these two expressions have to be equal to each other. And the result of this algebra is that we get the natural log of K1 plus activation energy E sub A divided by R times T1 is equal to the natural log of K2 plus the activation energy E sub A divided by R times T2. So again, this side of the equation I got from here, this side of the equation I got from here. Now what I'm going to do is bring everything with a K over to the right side and everything with an E sub A over to the left side. And this is what I mean by that. We get the natural log of K1 minus the natural log of K2 is equal to E sub A divided by R times T2 minus E sub A divided by R times T1. Again, I'm going to use natural log rules to combine this side of the equation right here. So from that we get the natural log of K1 divided by K2 is equal to E sub A divided by R times T2 minus E sub A divided by R times T1. Now what I'm going to do to the right side of the equation is pull out or factor out an E sub A divided by R. So we get the natural log of K1 over K2 is equal to E sub A divided by R times 1 over T2 minus 1 over T1. And now we are ready to solve for E sub A. So what we get is this equation. Solving for E sub A, we get E sub A equals the gas constant R times the natural log of K1 divided by K2 all over 1 over T2 minus 1 over T1. Plugging in our values, we get E sub A equals 8.31 joules per Kelvin times mole times the natural log of 1,000 seconds to the negative 1 divided by 2,000 seconds to the negative 1, all divided by 1 over 400 Kelvin minus 1 over 300 Kelvin. And then we just plug this into a calculator, and we get 6,912 joules per mole. So that's the activation energy for this hypothetical reaction with this set of data here. And so again, we were able to solve for the activation energy without even using the frequency factor A because we had two sets of data points. So if we were given the frequency factor A and the reaction constant K and the temperature T, we could have just solved for E sub A. But this is just another way of using this equation.